So let's start the next section, rates of change. Now this is nothing new to us, it's not a new idea. We have actually already come across two different types of rates of change, average rates of change and instantaneous rates of change. And the instantaneous one is just the notion of derivatives. Now besides developing and seeing the theory of derivatives, we have applied this notion here and there in places. Some of these applications are geometric in nature, where derivatives represent slopes of tangents to curves, but some other applications are where simply the derivatives are rates of change, that's all. But this section focuses mainly on applications. Okay, now when we think of the term rate of change, usually it indicates that the change is happening with respect to time. For example, the position of a moving object changes with respect to time, and its rate of change with respect to time is velocity. The rate of change of velocity with respect to time is acceleration. But that's not necessarily always the case. For example, a physician may be interested in knowing how the reaction to a medicine, the reaction of the body to a medicine changes as the medicine dosage changes. So here the dependence is not on time but the amount of dosage. An economist may be interested in knowing how investment changes depending on interest rates. In general, if we are given a function, then we can talk about its rate of change, or rather the rate of change of its values, its outputs, with respect to the inputs or independent variable, and that variable need not represent time. So let's go back to these ideas that we already know. Let's recall what average and instantaneous rates really were. Okay, so thus we start. The average rate of change of a function f of x over an interval from some x value, say x naught, to a neighboring x value, x naught plus h, is this ratio. F of x naught plus h minus f of x naught divided by change in the output value divided by change in the input value. The input value changed from x naught to x naught plus h, so that difference, and the new denominator reduces to h. So the rate looks like this. Okay, and the instantaneous rate of change of f of x at the point x naught, not in an interval, at the point x naught, is the derivative of f at x naught, which of course is the limit of these average rates as the interval becomes smaller and smaller in length, that is, as h approaches 0. Provided, of course, that the limit exists. Now the word instantaneous usually refers to instant, an instant of time. However, in this context, we use instantaneous to mean that we are calculating the rate at a point, and that point need not be a time value. Okay, it is some value of the independent variable x, which physically may represent anything. It may represent temperature, amount of medicine, anything. And because we are mostly interested in instantaneous rates of change, we omit the word instantaneous in fact, and we simply say rate of change. When we say rate of change, we have to understand that it's at a point, not in an interval. In other words, it's instantaneous rate of change, its derivative, not that average one. If you, however, want to say or consider average rate of change, you have to write that word average. Okay. So let us now see an example. This example comes from geometry. The area A of a circle depends on its diameter d, as you already know A equals pi times d square divided by 4. Actually, this one is not the more common formula for the area of a circle. More commonly we know it as pi r square, where r is the radius of the circle. But when you write d over 2 in place of r, because that's how radius is related to diameter, it's 1/2 of diameter, and take its square, you get this. Alright. Now, how fast is the area changing? When the diameter is 10 meter. This means that we have to know the rate of change of the area with respect to diameter, not with respect to time, okay. At the instant or at this value of the diameter 10 meter, that means it's average, it's not average rate of change, it's instantaneous rate of change. So we have to basically just find the value of the derivative of A with respect to D when D is 10 meter. We have, so this is what we have to find. Because pi over 4 is constant, so by the constant multiple rule of derivatives, it comes outside of the differentiation process, and we just differentiate d square, which by the power rule has derivative 2d. So pi over 4 times 2d, or pi d divided by 2. But units are given, so we have to express the rate also in a unit. Area has unit meter square because the length unit is meter and length has unit meter, so the rate of change has unit meter square per meter, or equivalently it's just meter. but we have to calculate this rate when d is 10 meter. So, the rate of change of area with respect to diameter when d equals 10 meter is this. If you are using prime notation for derivative means, in that case, you treat area as a function. It is a function, but you treat this a as the function name itself. Then your a of d looks like this. And then when you calculate its derivative, it's going to look like this. And then if you evaluate this derivative at d equal to 10, you will just write a prime of 10. But because we are using this notation, so evaluation is shown like this, is written like this. So if you substitute 10 for d, you are going to get 5 pi. Again, unit of course is meter square per meter. I think it's better to write like this. It clearly shows what we are dealing with. If you want, you can write meter, but that may be a little confusing. Okay, now a little, after this also the authors have written something. Let us now try to interpret this derivative, or let us see how we can relate this derivative with average rate of change. We already know this, that the limit of the average rate of change. What is the average rate of change in this case? It is delta A divided by delta D. Delta D is a small change in D value. Say the D value was this, and after something happened and the D value changed to that value. It is that difference. And the corresponding difference, if D changes, A will also change, and so there will be a difference of the corresponding A values as well. That is delta A. And delta A divided by delta D is your average rate of change of area with respect to diameter for that change of diameter. And the limit of this ratio as delta D approaches 0 is of course by definition our derivative of A with respect to D. Now if our delta D is really very small, if delta D is small. Now in mathematics, simply the words small, large do not have any meaning because they are vague words. But in a given context, you can call some things small. If delta D is very small, then delta A divided by delta D is approximately equal to the derivative. Why? Because that's what this thing is now. As your delta D becomes smaller and smaller, these ratios go towards a limit. So for infinitely many delta D values, you will get infinitely many ratios, and they are approximating the actual real number, which is the derivative. So as you choose your delta D smaller and smaller, this approximation becomes better and better. So for very small delta D, depending on how much accuracy you need, between your actual value and your approximate value, the approximate value will be close enough to the actual value. In that sense, this is approximately equal to this. Now, unlike this quantity, which really is not a ratio, it is not dA divided by dt. We have already talked about this. This is a ratio. So, we can multiply both sides by delta D and have, also with the assumption that delta D is not 0, we have this. This means that if there is a very small change in diameter, then the corresponding small change in area can be calculated like this approximately using the derivative. And that is why the authors, after finding this answer, write, so for a small change delta D meter, change in diameter, the unit is meter, so the change will also have the unit meter, in diameter results in a corresponding change. These are not the exact words of the authors, okay, but they have the same meaning. Change in area which is approximately what? What is this value? 5 pi. Pi times delta D, and area unit is meter square. Okay. And now after this we come to some other rates of change which are actually depending on time. And these are the notions of displacement, velocity, speed and acceleration that you saw in mechanics. Motion along a line. Displacement, velocity, speed and acceleration. Okay. Now we need to draw a diagram. Motion along a line. This type of motions has a name. They are called rectilinear motions. No matter how simple they sound, but there are many things in them also. If an object moves along a straight line, then it's called rectilinear motion. So this is the line along which our object or body, whatever you want to call it, is moving. And it's not an ordinary simple geometric line which simply is just a line without any end on this side or on that side, but it's a coordinate line, a line whose points have been given real numbers, or there is that association. To put things more simply, this is like an x-axis. This is a real line. That's what it is. For some reason we call it the s-axis. S denotes position. Now, what happens is that the object assumes this position, say, at some instant t of time, and the position is s, and this s is a function of time. This function tells us when the object will be where. What is the position of the object when the time instant is t? That question is answered by this function. At the instant t, the object lies here, and say the object is moving to the right. This is the direction of motion. At a later instant, say t plus delta t, the object assumes a new position, and that new position is of course given by the function f of t plus delta t. Say that new position is s prime. Do not get confused, okay? What is this s and what is this s prime? These are real numbers, and they are the corresponding points on that numbered line. Say this s is 1 for some t value. For a later higher t value, s prime is say 3 or maybe 100 if the object is moving really fast. Okay, so that's what they are. They are basically just real numbers. Now, if I take the difference of s prime and s and give it a name, what will be the difference? The difference is s prime minus s. Say I give this the name delta s, because delta s is a change in s value, which is what it is. Then in place of s prime, I can write what? S plus delta s, right? It's simple enough. And this delta s has a name. It's called displacement. Let us now write the things. Suppose an object is moving along a coordinate line, s-axis, so that its position s at an instant of time t is given by this function s is equal to f of t. At another instant t plus delta t, its position is, instead of writing this s prime, I am straight away going to write s plus delta s. Okay. Now we define displacement. The displacement of the object in the, when displacement from what point to what point, in the time interval from t to t plus delta t. is this. Now, before we say something else about this situation, let us observe one thing, okay. This delta S may be negative also. It's tempting to simply think of delta S as the distance between the two positions of the object during its motion at these instants of time. Yes, it is distance, but it is a signed distance. It comes with a sign. It may be positive, it may be negative as well. How? In this specific situation, the way we have drawn this diagram, it doesn't seem to be negative, because we are subtracting a smaller real number from a larger real number. It is positive, but who is restricting us to have only this type of motion? The motion may be in that direction also, no? In that case, what will happen is that as time passes by, say at the instant of time t, this is where the object lies. At a later instant, it will lie there. So the new real number you are going to get as the later position of the object will be smaller than this real number. Now from that smaller real number, if you subtract this larger real number, you are bound to get a negative value. So displacement becomes negative, it can become negative. And that is why this displacement, perhaps I should not bring this up right now itself, but still I am doing, is not a scalar quantity, it's actually a vector quantity. I will talk a little more about that, but right now let's just see what we have ahead of us. So this is what displacement is. Without thinking of vectors or anything, we understood that it can be negative. In some situations it can be negative. Now after displacement comes average velocity. Of the object in the time interval from, let me continue from that side. I need this diagram. Time become line, time interval from t to t plus delta t is, we write it as v suffix av. Av denotes average. Displacement divided by time. Although we have simply written time here, but it's the length of the time interval between the time instants t and t plus delta t. So this is delta S divided by delta t. Now if you write what delta S is, it assumes the form this. Okay, so that is the average velocity, not average speed. Okay, that is something else. This is the average velocity. Just like displacement can be negative, average velocity also can be negative. And in fact, it will become negative if the corresponding displacement is negative. Delta t doesn't become negative because time only moves forward. So At one instant you have the time value t, at a later instant it will only have a higher value. So, delta t needs to be positive. So, here the denominator is positive, numerator however being displacement can become negative, and that is how velocity also can become negative, alright. And after this, and because we are talking so much about positive and negative, what does it mean physically? This is the distance that the object covered in this amount of time. So, the rate at which this happens is the distance covered divided by time taken, and that is your velocity, but it can also become negative. Okay, that is possible, and it is also not simply the distance. You see the difference. Displacement and distance are two different things. Distance can only be 0 or positive. Displacement can be positive, negative or 0. There is a directional aspect to displacement, which is what makes it a vector actually. It is not exactly a scalar. But we will discuss about that later. Next, let us see the instantaneous velocity. We won't call it instantaneous velocity, but we are going to write the word instantaneous here just to emphasize the fact that its derivative. Of the object at the time instant t is derivative of the position function s equal to f of t with respect to t at t. With respect to t at t sounds a little confusing, because here t is a variable and that t is a constant. If you want, you can write something else here, t naught or something like that, but you get the point. That is, the instantaneous velocity, which is v of t, is just this ds dt, and that ds dt I think now I can get rid of this diagram. Is the limit of the average velocity as the time interval over which we calculate the average velocity becomes smaller and smaller in length as delta t approaches 0. Provided the limit exists. Whenever you give a definition which involves a limit, always write provided the limit exists. In that case only the definition makes sense. Otherwise, in other cases it remains undefined and it's not useful also. Alright. So that's what average velocity and ordinary velocity or instantaneous velocity are besides displacement. We still have to define speed and acceleration. That, however, we won't do today, because before that there are some somewhat long discussion involving some examples that we will do in the next calculus video. But before we end today's video, let us just talk about this vector aspect of this displacement and velocity. Say, for rectilinear motion only, so this is your S line or the real line or S axis. Because it's the real line, at some point you will put the real number 0. That will be the origin of your linear one-dimensional coordinate system. Now say the particle is here at some point, whose position is say S1. This happens at the time instant t1, second, minute, hour, whatever the unit is, and say at a later time, this is the position that the particle assumes, f of t2. Okay. Now, whenever you have a motion of something and you have decided on a coordinate system, because we are considering a very special case where the motion is along a straight line, it's rectilinear motion. So we have conveniently decided to consider the coordinate axis as the line along which the motion happens. So then what you do, these positions that the particle assumes or the object assumes at different instants of time are given by this function. Now instead of considering this simply they are real numbers, but you can associate with these real numbers some vectors. What will be the vector associated with this point? It is that vector whose initial point is always at the real number 0. And the terminal point is where the point is, at S1. This vector is called the position vector of this, not that point but the object. So as the object moves, this vector also moves. The vector can become larger or smaller in magnitude depending on how far or close the object is to this origin, and also it can lie on that other side also. So the vector can be negative as well. For example, the position vector of this position of the object is this. So now when you calculate the displacement of the object, say you assume that t2 is a later instant of time. What is the displacement in the time interval t1, t2 of this object? This is S2 minus S1. Now you can think of S2 minus S1 as just the difference of these two real numbers, but you can also think of them as the difference of two vectors. If you are if you are means you already are familiar with vector addition, vector subtraction. In that, if this S2 is further away from the origin than S1 is, which also I think the diagram indicates, then the difference will be a vector something like this. Because S2 minus S1, if S2 is larger than S1 and S2 is negative, S2 minus S1 will itself be negative and lies here somewhere. Okay, so that way this will be your displacement vector. And when you divide a displacement vector by the length of the time interval, what exactly are you doing? You are dividing a vector by a real number, or you are multiplying a vector by the reciprocal of the time interval, which is also a real number. And we multiply vectors by real numbers. Scalar multiples of vectors exist. I mean, that operation is there. What is the result of that? Again, a vector. So that's how every average velocity is a vector. And as your delta t becomes smaller and smaller, your average velocity as a vector changes. And these vectors approach some limiting vector. That limiting vector is your instantaneous velocity, which is also a vector. If you do it in one-dimensional space like this, it doesn't really become apparent. We don't really need to think of these quantities as vectors because the real number system takes care of everything nicely. But if you do it in plane or in space, say your motion is quite complicated, it's along a space curve like this, then the position vector will change in whatever direction it can change. But there also you can calculate average speed, average velocity like this, and there also you can take limit, but that cannot be handled by this simple notion of limit. That needs an extension, and you go to vector calculus, which is what you need if you really want to even start studying physics. It is there in this book itself. At some point we will come across these things, and then we will be able to do many things. But here also in rectilinear motion also, if you carefully go through these things, we will be able to solve many mechanics problems, and we are going to solve, okay, as the examples are coming and the exercises are also coming. The point is that whatever you do, always try to think of everything rigorously. Do not lose track of why something is like this. If you get stuck somewhere, keep thinking about it until it becomes really clear what it really is. Okay, so we will see more about this. These applications are extremely interesting, and it's going to become even more and more interesting as we go to the other parts of this book. In fact, in this section itself, towards the end, there are applications of these ideas, not these ideas, but the notion of derivatives, to economics. Okay, so we will see these things, but in the next calculus video. And tomorrow, as usual, we have our linear algebra. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.